we apply the boundary condition for this metal box, which has 4 boundaries. Boundaries number 1, number 2, number 3, and number 4. Okay. For boundary number 1, what is boundary number 1? Boundary number 1 is s equals to 0. Okay, on this coordinate system, if this is x, this is y, and then how long it is? It is z. X, y, and z. For this x, for boundary number 1 means x equals to 0. Okay? On this boundary, what is the tangent E field on it? The tangent E field is EY to the y direction. So EY equals to 0. Okay? So boundary number 1, let me write down here. X equals to 0 and EY equals to 0. OAE, give you chance to answer. Boundary number 2. Yeah. So boundary number 2. What is boundary number 2? Y equals to what is it? Huh? Y boundary number 2 here. What is boundary number 2? Would you speak louder, please? Huh? Number 2. Okay, come to write down. Come to write down. I cannot hear you. Peng Hao, number 3. Zhong Tingjun, number 4. Okay. Boundary number 3. Boundary number 4. Write down, and we will check the answer. Write down here. Just write down number 3 here. Here. I will use that, so you write down here, and the number 4 write down here. What? That's it?
No.
You are not listening my class, right? Are you? Yes. Okay. Good. Okay. Okay. Wei, good job. Number 3. Y0, EX0. Okay, good job. Okay, is B. Okay.
Very good. Okay.
Good. For boundary number 1, EY equals to 0, or maybe I don't use a vector, I use a scalar, it's okay. What is EY? Now we go back to see EY. What is EY? EY, right? For for TE mode, EZ equals to 0, right? So EY equals to J over KC square multiply, because this is 0, so you have only this term. Omega mu over HZ divided by X. Okay. And what is HZ? HZ is small hz multiply the exponential term. And this is not important. This is not relevant. So small hz is more important. And the small hz is capital X and capital Y equals to this term. Okay. First of all, we know J is not 0, right? J, of course, is not 0. We know Kc is not 0 here because this is a TE mode. Omega is our frequency, mu is from your material. So if you want to know this one equals to 0, what can obtain? What we can obtain from here? So we take the derivation to x to this term. Equals to, this is not equal. The only thing we try to understand is we try to derive x, right? So actually the only thing important change to only this part. We take a derivation of this one, this term, only the x part, because this is y, right? And we only get rid of, we try to focus on only x component. So what is this one? This one should equals to 0. We can write down like this one. Because EY is 0, so this term equals to 0. Okay? Then, what is 0? Okay. So it is A, K, X minus sine KXX. It's time to review your calculus, right? B, K, X cosine KXX equals to 0. And we know x is 0, right? Boundary condition. This one is 0 and x is 0. Sine 0 means 0. Cosine 0, it is 1. Bkx equals to 0. Guys follow? This is 0 because sine 0 is 0. This is 1 because cosine 0 is 1. You left only this term. Bk equals to 0. Okay? Okay. We try to solve what is ABCD. So here we know B equals to 0. This one is maybe, we try to calculate this later. So, but we don't know B, right? So from boundary condition 1, we obtain B equals to 0. Okay. There are many assumptions we try to make, try to understand why he can become 0, why he cannot become 0. Okay, Kx is not 0 because we are trying to calculate it. That's why the only term B we try to find out is 0. Okay. Boundary condition 2, x equals to a, ey also equals to 0, and we know b equals to 0 from boundary condition 1. We do the same technique here. We know ey the same, so we did partial x to x equals to, I should not erase it because the same result. A minus a kx sine kx plus bkx cosine kx equals to 0 when x equals to a. Boundary condition 2. Okay? So, but I know from boundary condition 1, I know b is 0. So I don't have this term anymore. B is 0. And for this one, it's 0. And a equals to, x equals to a. Okay? What is the sine function? Sine theta. Theta. This is pi to pi. When is 0? When kxa equals to 0 or pi or 2 pi or 3 pi, 4 pi, and etc. When Ka equals to some integer multiplied by pi, this one is 0. Okay? We can write down like when Kax equals to some number, integer number, 1, 2, 3, 4, or 0, 5, multiplied by pi. Okay, we assume we make this simpler. M is a number. Okay. So, Kxa equals to m pi. Kxa equals to some number multiplied by pi. Okay. Boundary condition number 3, if y equals to 0, then Ex equals to 0. Okay. Similar to this equation, and because we are now going to read through the y, right? So we will see this part. When this y is 0 and this y is 0, this is also the same. This sine part becomes cosine and becomes 0, so means d equals to 0. Very quick. We got a very quick answer, similar to boundary number 1. And we also get a very quick answer from boundary number 4. We have very similar result. We know k, y, b equals to another number multiplied pi. Because you have cosine, sine, cosine, sine, very similar, right? So your result is totally the same. When we say this is a mole, TE10 mole, or TE some number mole, this means M. Oh, sorry, MN. If I say this is TE10 mole, 10 mole, it means we take the answer of m equals to 1 and n equals to 0. All of this answer, all the combinations from the integers of m and n can propagate a mole E field inside a waveguide. So there are more than one possibilities. There are many possibilities to propagate. So the number m and n is how we name the mode. Okay, so this is the result is important. The result is important. Actually, you know which one you are trying to calculate. You know your kx equals to m pi over a, and your ky equals to your m pi over b. And back to your definition of kc. So you can calculate your cutoff frequency, a cutoff wave number kc squared equals to pi m pi over a square plus m pi over b square. M and n are decided by your number of solution. You have TE10, TE01, TE11, TE2, it depends on the number. So you can calculate your cut-off wave number by this equation. Okay? And your KC is KC square. It is K square, which is omega square mu epsilon. If it is air, you use the mu 0, epsilon 0. If it is air inside, minus beta square, right? So, what is the beta of this waveguide? It is, you can calculate the cut-off wave number from the mode you decide. You obtain KC. You have material, you have K square. You can understand what is the beta, then you can find lambda G equals to 2 pi over beta. You can find out the wavelength of your waveguide. And you can decide a half wavelength waveguide as your resonator. If the length is AB, call this D, equals to half wavelength, it can become a resonator and resonate. And you can become a component to design a filter. Okay, but how long it is, how to calculate that, you will see that in your final exam. Okay, actually I try to explain everything already. Alright? Are we good? Good? Okay, let me finish a little bit more. This is how wave propagate in the waveguide. We just carefully see this picture. Okay. So if it is a TE, maybe 1 ohm more or 2 ohm more, M ohm more, okay, it means you have your E field in this direction. Okay, for your E field, it's okay. The problem is your H field. The H field is blue one. If this is a TEM mode, H field is also on the same plane. But your H field is a combination of this direction and also the Z direction. So your blue one, your H field is going to a little bit forward. Okay? The blue one is your H field. Okay, let me use this one. If this is a cross section of the waveguide, okay, and this is B, and this is A, and this is B, okay, this is cross section, and your E field is on this plane. Okay, red one. E field. The red one is E field, okay? The E field is on the cross section, okay? And your H field has two components. You have not only the component on the plane, but also a component to the direction you propagate. This is your E, and this is your H. You have not only the vector on the plane, but also you have a vector to the direction you propagate. Okay? So, what is the total H field? So the total H field is in this direction. It's not just on the plane, but not only to the Z direction. It's like the middle. Okay. So the black one is the propagating, the P, the pointing vector, the direction of pointing vector. You still need to consist pointing vector theory. I think my direction of H should change. So if here and here, this direction and this direction can become this direction for H. So your direction of P is this direction. It's a little bit between Z and I think it's the plane. Okay. So for this combination of E and H, actually the direction is here, but your power is also moving, propagating to Z direction, but actually this is, it's like jumping, reflecting by your metal wall. Okay, this is for TE N0, and that is for TE0N. So that's why you need to come to class and see, because I need to show you use this 3D model. And this is how we derive. I just put that on the PowerPoint. You can see those are everything I written on the whiteboard for everything. And for this case, for TE mode, EZ equals to 0, and also your HZ is small h multiplied the exponential part. And you write down this term, and then we start from the next equation, right? And then we use the separation of variables. We set small h equals to capital X and capital Y. We separate the X part and the y part. And we use the wave equation. We know the answer of x and y were similar to our wave. So we also apply the Euler rules to separate cosine and sine part from that. Okay, do the same thing here. So your h equals to AB multiplied CD. And then you apply also the boundary conditions. You know the tangent E field equals to 0 for 4 boundaries. You do the differentiate to hz respect to x and y. You make them equals to 0, and you put x equals 0 and a, y equals to 0 and b for the for 4 different boundaries. You solve these equations to obtain b and d are 0, and a and c, you want to make them equal to 0. You want to make them the term of sine and the cosine, the term of sine equals to 0. You obtain your kx equals to n pi over a, and your ky equals to n pi over b. And small m and small n, they are the numbers for TE mode, the different answers. Okay, I just quickly review the answer. And finally, you have the cutoff wave number for x direction and y direction depending on the physical length, your A and B. It is how many times of the pi, because you want to know that it is a sine, right? Sine wave to make the sine equals to 0. After you do that, you can calculate beta. You can calculate color wave number, and because you know k equals to omega multiplied the square root of mu epsilon, you can obtain beta. Do the same thing. Actually, I repeat everything again. So your kc equals to this one, and then your beta equals to this equation, right? It's just simple math. And because your kc equals to half of angular frequency multiplied square root of mu epsilon, so which is 2 pi fc for your omega c. Okay? You can find out your color frequency from the equation. It depends on which mode you try to solve. And this equation, Kc, is how we make this table. We have cut of frequency. You put your number m and n inside, you can solve these numbers, and then you can determine which mode will show up by these numbers. That is the Fc is the equation for these two. For the table, for the first and the second, it depends on how many modes. You just put all the numbers, and also you also have the mode for Tm mode. Can you guys follow? go back to what we want at the beginning. We want a total E field and H field. But we need to obtain our HZ, right? Because we know B and D, they are 0, and we assume another magnitude that A multiplied C is A M N. We name a new unknown here, but we know for this term it is a cosine, and we know Kx equals to n pi multiply A, and we know Ky equals to n pi over B. So you can write down the final form of your HZ. And after you know your HZ, you can put them back to all these 4 equations, can find out all other field. Then you know your total E field is this 3 term. For TE mode, you don't have this term. It's 2 term. And the H field is the summation of these 3 terms. And those are the answers. Okay? Big work, huh? When you derive, it's huge work. 3 weeks derivation to make you understand, to expand everything. Actually, if you want to understand this one, we should start from the start of this class, right? The first week. We use the boundary condition, we use the wave equations, we explain how the wave works, right? All the E field, H field, everything. Then you can explain how it works for a simple rectangular waveguide. And those are the answers. You can use the answers, the equation. That's why this exam is an open book exam. So just put a number in, and you know TE E0 mode, EX equals to 0 because it is cosine the sine. Sine 0 is 0, right? And for EY, you have this. For HX, this one. For HY, also 0, because sine 0 is 0. And for HZ, you should have some number. These are the total E field and H field for TE E0 mode. So I just simplify it. I just write down the result of that page. So EX equals to HY equals to 0, and the EY is this one, HX and HZ. And this is how it works for the TE E0 mode. You can see this is if this is a cross section of waveguide, so this is A, and this is B, and this is L, this is D. A and B, A is the longer one, and for this one is, I think it is, okay, this one is to C in this term. The cross section of the whole. Okay, then you can see in the middle of that, there is a look like a sine function. In the middle is the strongest. Okay, also the same as H. The direction is going to EY, right? Because the EY is a function of sine. So this one is there is a half. You can see the sine. This is the cross section. This S and the Y. The middle is larger because EY is a sine function, and there is no EX. Okay, and for HX is also a sine function. Let's
手游也能有大荧幕体验，《异域战记》新上线，超华丽战斗画面，大荧幕给你动画般的享受。立刻下载 Google Play 游戏，用电脑玩《异域战记》，体验大荧幕的沉浸享受。
立即下载。
This is how the TE10 mode works. You see a task is a sine. TE10 mode. And for the second one is from the top. This one you can see from the top. This one and this one is from the cross section. And for this picture is from the side, the E field. TE10 mode. For the fundamental design of the waveguide filter, we use TE10 mode at the beginning because it is the main mode, primary mode, the fundamental, most basic mode. So TE10 is most important. Okay. You can see it is moving, right? Moving to the Z direction. You can see the E field, and this is the H field. And you can also see other modes. TE11. Okay. So for other mode is too complex. Maybe you can use the math, and you need to read more carefully. Okay, there are many other different modes. Okay. And so TE, TM, then you have the answer, the equation for everything you need. You have table in your textbook, in Posa, right? Everything. So I can ask you any question, right? About any more, and you can give me the answer. This is how they draw. I think the animation is more vivid to understand. This one is hard to understand, right? Use a picture. But if you have only paper and book, this is the only thing you can do. But we have a lot of tools like HFS, CST. You can always see how the wave move for different modes. You can set up, try to use the simulators, right? And that's it. So I make some assumption, conclusion about the whole this semester. Okay. So you have a coaxial cable, you have waveguide. Maybe we can skip the strip line, we just already go to micro strip line. It is the mode for coaxial cable. You usually use a TEM mode, but actually in coaxial cable, you have TM mode and TE mode inside as well. For waveguide, you choose TE10 mode. Okay. It's good because you will know why. It's okay, but it's not easy to understand if you get rid of my class. Okay, let me finish it. Let me finish this last part. TE10 mode is the most primary, most basic mode for the waveguide. But you also have TM mode and the TE mode. Okay? And for the microstrip line, it's quasi-TEM mode. Okay? And we didn't discuss about dissipation. Maybe in the future, we will have time to discuss about that. For the dissipation is, because if your beta is changing, depend on frequency, your velocity is changing, depend on your frequency. So your wave will arrive, you use a different velocity, your wave can arrive in at different time. So this is a dissipation. This is more complex than what we learned so far. I only introduced the most useful element about microwave engineering, but that doesn't mean that's it. There are always much more than that. I only introduced you 3 chapters. Those are the basic outline. Those are just only the outline. Okay? And the bandwidth, so you have different bandwidths and different nodes, and you can read through all that. How to integrate, is that easy to integrate with other? It depends on what are the other circuits. That's it for our test class. Okay, and why I insist you to come here, because I will give you a gift today. So because I think maybe all of you is okay. I will just give you a final exam take home. You turn in your exam next week before the noon 12 to my office. You write down your answer. You can spend your time, but no discussion about the final exam. Is that okay for everyone? So now everyone come here, right? Right? That's why you should come here. If you don't come here, you don't have final exam. Or maybe you should have exam by your own, only 3 hours. Everyone can spend 1 week. Is that okay? Is that good, right? It's better than open book, right?
老师可以用中文讲一下。
Want me to translate? Okay, please allow. 给你们回家写。